In the last example, I went over how to find individual forces at a single point within a beam. However, it's frequently useful to know all of the forces in the beam as a function of distance. In this case, we're going to draw the load shear moment diagram for this beam. That will give us a set of equations for the load, the shear force, and the moment within that beam as a function of distance away from point A. So that's once again going to be our origin here. The first step is to draw a Freebody diagram of the entire beam and solve for support reactions. Since this beam was supported by a pin at point A, we're going to have two forces, an X and a Y. At point B, there was a roller, so we'll have one force perpendicular to the surface at the point of contact. Notice that I've also labeled point C here and point D over here. Now, as I said, next we'll solve for support reactions. So here you can see I've solved for each of the three unknowns independently. I've solved for AX using some of the forces in the X direction, for AY using some of the moments around point B, and for BY using some of the moments around point A. I do recommend that you find support reactions using independent solutions because it makes the rest of your work a lot easier to check. Also notice that once we find a value for your support reactions, you have to accurately record that throughout the rest of the problem. We typically use a load shear moment diagram to depict the load, shear, and moment acting on the beam. The load diagram is very straightforward. This first line is nothing more than the beam itself with all the loads and moments applied to it. From there, we can develop the shear diagram. Now in this case, because the load diagram is so simple, because it only consists of point forces, we can immediately go from the load diagram to the shear diagram. I will show you an example where that's not the case. Anytime there are distributed loads, that can't be done. But in this case, we can do that very easily. When you see a point force on the load diagram, it immediately causes a change on the shear diagram of that same value. So when we see a positive 3.5 in the load diagram, we get an instantaneous change in the shear diagram of 3.5. So here's our positive increase of 3.5, and because nothing happens in the load diagram between points A and C, the shear diagram will stay the same between A and C. Now at point C, there's a negative 18 kilonewtons applied on the load diagram, which will cause a negative 18 change in the shear diagram. One more thing I want to point out, the area between 2 points will tell us the change in value between those 2 points. So in this case, there is no area between C and B, so the value between C and B on the shear diagram will not change. Over here, BY is a positive 20.5, so on the shear diagram we'll see a change in value from negative 14.5 to positive 6. And the final thing that happens on the shear diagram is DY pushes it down, so we are at 6, DY pushes it back to 0. A few things to note about the shear diagram. All of these point forces produce an instantaneous change in the shear diagram that's equal with value and sense. Also, the shear diagram and the bending moment diagram will always start at 0 and end at 0. So it's important to note that when we end at 6 over here, there's got to be something that pushes it back to 0. And the last part is that moments applied on the load diagram do not directly affect the shear diagram. Now I say directly because that moment did affect the value of the support reactions here, but it does not directly produce an instantaneous change in the shear diagram. Now on the moment diagram, the area above tells us the change in value below. So the area of this rectangle, it's a rectangle, and its area is 2 meters wide and 3.5 kilonewtons tall. So 2 times 3.5 is 7 kilonewton meters, which means the bending moment diagram will change from 0 to 7 kilonewton meters in the positive direction because that was a positive area. Now this next area here is 2 times negative 14.5, which would be negative 29. So that means that this changes from 7 to a negative 22. The next area is a positive 6 times 2, which would be a positive 12. Negative 22 plus 12 is going to give us negative 10. As I said before, a concentrated moment on the load diagram will produce an instantaneous change on the moment diagram. The last part of this is to define this distance. Anytime any of these diagrams cross the x-axis, you need to say what location they cross at. The shear diagram already has its locations marked. It crosses the x-axis at 2 meters and at 4 meters. Once again, those are both measured from the left side of the diagram. The moment diagram, however, crosses the x-axis here, and it's not indicated what distance that is, so we have to mark it. We have to calculate it. There are a couple of ways to calculate this distance. Probably the easiest one is to use similar triangles. Here, this larger triangle we has a height of 29 and a base of 2. We have a smaller triangle right here, which has a height of 7 and an unknown base. So we can then set up in a ratio. If I call this base distance d, my equation would then be 2 over 29 equals d over 7. Solving that equation for d will tell me that d equals 0.4828 meters. Now be very careful, because that distance d is just the base of this triangle. So this distance here to where it crosses the x-axis, I'll call that distance x, and x equals the 2 meters already given plus that distance I calculated. So this x distance is 2.4828 meters. For these load shear moment diagram problems, the answer actually is this entire load shear moment diagram.